a singular value, a singular value decomposition. Okay, a singular value decomposition of a matrix, of a matrix. Okay, of a matrix can be used to can be used to factor can be used to factor, okay, a square matrix, used to factor a square matrix. Understood? Then what happened? Then here we also write it now. That means a complex number as a product of complex number and a non-negative number. Okay, a complex number, a complex number as a product of as a product of as a product of a complex number of length 1, product of a complex number of length 1 and a non-negative number and a non-negative number. Okay, then what happened in case of matrices? Okay, we write it here in this way. In case of matrices, in case of matrices, what happened? The, that means the complex number of length 1 replaced by a unitary matrix. The complex number of length 1 is replaced by a unitary matrix. Okay, and the non-negative number is replaced by and the non-negative number and the non-negative number is replaced by a positive semi-definite matrix, a positive semi-definite, okay, matrix. Understood? So we now write this theorem here for the polar decomposition. We now erase that portion and going to discussion theorem. Okay, we write it here theorem polar decomposition. Okay, here for any square matrix A, for any square matrix A, okay, there exists a unitary matrix W. There exists a unitary matrix here W, okay, and a positive semi-definite matrix P and a positive semi-definite matrix P such that such that what A equal to WP. Okay. Furthermore, okay, if A is invertible, A is invertible, then the representation is unique. Then the representation B is unique. Okay, then the representation is unique. We now prove it. Okay, but I did prove here and going to discussion of some proof now. Then what happened? By theorem of the singular value decomposition theorem, by singular value decomposition for linear transformation, for linear transformation and obviously for matrices. Okay, but for matrices there exist unitary matrices. Okay, unitary matrices here U and V, and a diagonal matrix and a diagonal matrix. Okay, this capital sigma with non-negative diagonal entries, with non-negative diagonal entries, such that A equal to U capital sigma V star. Okay, then what happened now? Then we also write it, we erase our portion and go into further discussion of that. Okay, we write it in this way here. So A equal to U capital sigma V star and equal to U V star, here V capital sigma V star. Okay, then what happened? This one equal to W, this one equal to P. W equal to U V star and P equal to V sigma V star. Okay, then we write it what? Since W is a product of of unitary matrices, okay, then W is unitary, okay, and since this capital sigma is positive definite, is positive semi-definite, okay, and P is unitarily equivalent to, and P is unitarily equivalent to, here this capital sigma. Okay, so P is semi-definite. So P is semi-definite. Understood? Then what happened now? Then also let's discuss now what that means. Suppose A is, we discuss uniqueness part. Now suppose that A is invertible. A is invertible and factors as the product. Factors as the products. As the products. Okay. A equal to WP equal to Z. Okay. Where W and Z are unitary. Where W and Z are unitary and here and PQ are positive semi-definite and PQ are positive semi-definite. Okay, semi-definite, not a problem at all. So we now erase that portion and going to further discussion of that. Okay, since what happened is here, since A is invertible. Okay, since A is invertible and it follows that that P and Q are positive definite. P and Q are positive definite. Okay, and invertible and invertible. Okay, and therefore and therefore here Z star W equal to QP inverse. Okay, thus QP inverse is unitary. Here thus QP inverse is unitary. Okay, and so I equal to QP inverse star, here QP inverse. Okay, equal to here P inverse Q square, here P inverse. Okay, then what happened? Hence P square equal to Q square. Okay, since both PQ are positive definite, since both P and Q are positive definite, P and Q are positive definite. Okay, it follows that P equal to Q. It follows that P equal to Q. Okay, and therefore W equal to Z. Okay, then what happened? Then the factorization be unique. Okay, then factorization be unique. Okay, now we also then write about this factorization. Then the factorization of a square matrix as WP is called a polar decomposition of E. Okay, we now use that portion and write one definition. Okay, in this way we write it here. The factorization, the factorization, okay, of a square matrix, of a square matrix A as WP, where W is unitary, where W is unitary, and P is positive semi-definite, and P is positive semi-definite. Okay, then what happened? It's called a polar decomposition. It's called a polar decomposition. It's called a polar decomposition of A. Okay, the factorization of the square matrix as WP, where W is unitary and P is positive semi-definite, is called a polar decomposition of A. Understood? Now we discuss one related example here. Okay, we write one example. Here we also discuss the polar decomposition of A. A equal to 11 minus 5 minus 2 10. Okay, then what happened? We begin find singular value decomposition of A. Okay, then we find an orthonormal basis. Okay, that means to find an orthonormal basis. Okay, beta, basis beta for R square, for R square consisting of eigenvectors, consisting of eigenvectors, consisting of eigenvectors of A star A. Okay, then what happened? Then v1 equal to 1 by root 2 1 1 1 minus 1, and v2 equal to 1 by root 2 1 1. Okay, understood? Are orthonormal eigenvectors, are orthonormal orthonormal eigenvectors of eigenvectors of A star A. Okay, A star A with corresponding eigenvalues. We erase our portion. Okay, we write it here with corresponding eigenvalues. with corresponding eigenvalues. Okay, lambda equal to 200, lambda 1 equal to 200, and lambda 2 equal to 50. Okay, so beta equal to v1 v2, so beta equal to v1 v2, okay, is an appropriate basis, is an appropriate appropriate basis. Okay, then what happened? The sigma 1, the sigma 1 equal to root 200 and sigma 2 equal to root 50. Okay, equal to here 10 root 2, here 5 root 2. Okay, are the singular values of A, are the singular values of A. Understood? So we have what? We write it now. So we have, okay, V equal to 1 by root 2 minus 1 by root 2, here 1 by root 2, here 1 by root 2. Okay, and this capital sigma equal to 10 root 2 0 0 5 root 2. Okay, then what happened now? Then we also discuss here, that means we write it in this way. Then we find columns u1 equal to 1 by sigma 1 ev1 equal to 1 by sigma 1 equal to what? That means 1 by 10 root 2 av1 equal to, okay, we also, that means here 11 minus 11 plus 5 16, okay, 16 by root 2, and then here obviously again minus 2 and minus 10, minus 12 by root 2. Okay, then this one equal to what? Equal to 1 by 5, here 4, okay, and here 3 minus 3. Okay, then in this way u2 equal to what? We erase that portion. And u2 equal to 1 by sigma 2 av2. Okay, here 1 by sigma 2 equal to 5 root 2, av2 equal to here a 11 plus 16 by root 2, and here 11 minus 5 6 by root 2, and here obviously that means minus 2 plus 10, that means 8 by root 2. Okay, then what happened? 1 by 5, here 3 4. Okay, so then what we get? Thus u equal to here 4 by 5 minus 3 by 5, here 3 by 5, 4 by 5. Okay, therefore we have what? We have W equal to U V star equal to what? U equal to this one, 4 by 5, 3 by 5, minus 3 by 5, 4 by 5. U and V star equal to 1 by root 2 minus 1 by root 2. Okay, 1 by root 2. Here 1 by root 2. Understood? Just V transpose. And then this one equal to what? Minus 4 by 5 root, and here 3, then 7 by 5 root 2. Okay, then 1 by 5 root 2 common, then here 7. Okay, and then here minus 4 by 5 root 2 minus 3 by 5 root 2, that means 1. Minus 4 plus 3, 1, minus 1. Okay, minus 3, 4, that means 1, plus 3, 4, 7. Okay, so we get W equal to this one, U V star. Okay, W equal to what we get? U V star. And again we write it in this way. What happened here? That means we write here P equal to V capital sigma V star equal to what? Equal to, in this way, 1 by root 2, 1 by root 2 minus 1 by root 2, 1 by root 2. Okay, and here 10 root 2, 0, 0, 5. Okay, and here 1 by root 2 minus 1 by root 2, here 1 by root 2, here 1 by root 2, equal to what? Equal to 5 by root 2, here 3 minus 1, minus 1, 3. Okay, in this way we also discuss this one. Okay, then today we also discuss the polar decomposition of a square matrix and related example. Okay, so today I stop here. If you get this type of video, please subscribe my channel. If you have any questions, comments, suggestions, write it in comment box. If you want to give like, please click on like option. So today I stop here. Thank you.